The Wafi-Golpu Joint Venture, WGJV, an unincorporated 50-50 joint venture of subsidiaries of Newmont Corporation and Harmony Gold Mining Company Limited, is looking to progress the Wafi-Golpu project, the proposed development of a world-class underground copper gold mine in the Morobe province of Papua New Guinea. This fly-through shows the proposed mine and related facilities comprising the project. The mine area is located approximately 65 kilometres southwest of the city of Lae, on the northern side of the Owen Stanley Ranges. The project footprint will extend from the mine area around Mount Golpu to the coastal area in Lae Port and Wagang, with an infrastructure corridor linking the two areas following the Watut and Markham valleys. The mine area, which is the subject of a special mining lease and ancillary tenement applications, will host underground access, ore processing, power generation, accommodation, and other ancillary facilities. Due to the mountainous terrain, some of these facilities, like the construction accommodation area, a potential power station and the laydown area, will be located in the lower Watut Valley. Other facilities must, by their nature, be located near to the ore body, the main underground mine access at the Watut Portal. The process plant and the Ferre camp will all be located on the escarpment above the lower Watut Valley, at an elevation of 200 metres. A secondary underground access point, the Nambonga Decline, will be located closer to Mount Golpu. This access point will also serve as an important part of the mine ventilation system and will provide initial exploration access to establish an underground drilling platform to support further advanced geological and geotechnical data collection. It is proposed to utilise a mining method known as block cave mining. The main environmental benefit of this type of underground mining is a reduced environmental footprint compared to open-cut mining. The underground block cave mine lies below Mount Golpu, and a subsidence zone will develop as mining progresses and will break through to the surface about 3 years after ore production starts. The subsidence zone will expand gradually over the life of the mine to an estimated diameter of 1,000 metres. The Golpu copper-gold ore body is the dark near-vertical column-like mass that starts 200 metres below the surface and extends to depths of over 2,000 metres. The ore body is about 400 metres wide and well suited to the block cave mining technique. Offsets in the vertical profile of the ore body are caused by faulting. The main access to the ore body will be via the Watut Decline, comprising twin tunnels, that extends 4.6 kilometres to reach the bottom of the first caving level, BC 44. As decline development or tunnelling advances only a few metres per day, it will still take 5 years before the first ore is produced. Over the life of the project, more than 100 kilometres of tunnels will be developed, which will make the proposed mine the largest underground mine in PNG and on a world-class scale. The secondary access, Nambonga Decline, is shown as a spiral formation. The red ring above the main ore body is the cave engineering level that will be used to monitor the growth of the caved broken rock column. This will also be an important interception point for removal of underground water, a process called dewatering. Below this lies the 3 extraction levels, which are shown as solid green discs. The uppermost of these is called BC 44, which lies some 1.3 kilometres below the surface of Mount Golpu. This will be the first block cave mined, peaking at some 16.8 million tonnes per year and having a production life of some 7 years. Below this are 2 further block cave levels, called BC 42 and BC 40, each 200 metres apart. The period of mine production from all 3 block caves is estimated to be some 28 years. We now look at how block caving works. The method involves the undermining of the ore body to make it collapse under its own weight, forming table-sized boulders. The rock is directed into a series of funnel-shaped excavations to enable extraction. Drilling and blasting is used to undermine the ore body to form what is called the undercut level. This is then connected to an extraction level via a series of funnel-shaped drawbells. The extraction level is strengthened by steel and concrete reinforcing. Loaders, called LHDs, which stands for load haul dump, recover the broken ore, and take this to centralised underground crushers that reduce the rocks to a more manageable football size, suitable for transport to the surface. This transport is via a series of conveyor belts, which is shown as the green zigzag line extending from each of the levels. The conveyor goes through a series of transfer stations before travelling up the Watut decline to take the crushed rock to the surface, exiting at the portal. The underground activities are fully supported by underground infrastructure, like the workshop, which allows all equipment to be cared for and maintained underground. That means that the mining fleet does not have to travel up and down to the surface every day. The crusher chamber contains a gyrating crusher, which crushes the rock between a circulating steel core and the wall of the crusher. The crushed rock collects at the bottom in the crushed ore bin, and then it is fed onto the conveyor belt. We now zoom in on the conveyor transfer station, which enables the change in direction for the conveyors at each level. Crushed ore on one conveyor drops down onto the one below via a chute, and then continues up the receiving conveyor. Two other very important underground systems are the water pumping and cooling and ventilation systems that enable people to work safely deep underground, where it can be both hot and wet. These systems must operate 24 hours a day, 7 days a week, requiring a 99% reliable power supply to keep running and ensure a safe working environment. Following the conveyors back up the Watut decline to the surface portal area, we see more of the critical underground ventilation system infrastructure, namely bulk air coolers, cooling towers, extraction fans, and refrigeration machines. The conveyor delivers the crushed ore to the cone-shaped pile called the coarse ore stockpile. This sits next to the layered startup ore stockpile, which is a temporary stockpile used to hold ore that is extracted during the initial construction of the decline and underground development. To the left of the ore stockpiles are some important environmental controls for water management, namely the silt traps, raw water dam, and sedimentation pond. These facilities help to manage water and sediment from the process plant and portal terrace. During construction, treated mine water, including treated sewerage, will be reused for mine services where possible, and excess will be discharged to the lower Watut River or Nambonga Creek. During the operational phase, treated wastewater will generally be used in the process plant, with additional water needs met by the extraction of water from the lower Watut River. It is estimated that this extraction will be less than 1% of low-level flows. We now move around the southwestern side of the process plant, where the primary and secondary grinding facilities are located. This consists of a central semi-autogenous grinding or SAG mill and a smaller ball mill on either side. These grind the ore into a fine powder, like flour, to make it easier to separate ore minerals from waste minerals, which later become the tailings. An important feature of the proposed mine is that material extracted from the underground block cave after startup is processed in the process plant. That means apart from some small managed facilities during underground decline development, there will be no ongoing waste rock and no need to develop large waste rock dumps like at open pit mines. The finely ground ore is mixed with water and some collector chemicals like detergent that form large bubbles inside flotation tanks called the pyrite and copper roughers. In these tanks, the valuable copper-rich minerals are physically separated by sticking to the bubbles and float to the surface where they are collected, whilst the non-valuable minerals sink to the bottom of the tanks and report to the tailings. Cyanide will not be used in any of the processing. The separated valuable ore minerals become the concentrate. The non-valuable minerals that sink to the bottom of the roughers form the tailings stream. The two streams flow into two large tanks in the centre of the process plant called the concentrate thickener and the tailings thickener. These tanks remove excess water so that the respective mixtures can be efficiently transported 100 kilometres to the coast by pumping in plastic-lined, thick-walled steel pipelines. We now look at the pipeline infrastructure corridor in more detail. The picture shows pipes during construction, before they're installed and buried. There will be 3 pipelines. The larger tailings pipeline, which is 700 millimetres in diameter, about the size of a 44-gallon drum, and 2 smaller 200 millimetre pipelines, one that conveys intermediate fuel oil to the power station, and the other that transports the concentrate to the port at Lae for export. all of the pipelines will be buried at least 1.2 metres below ground. Looking at the pipeline infrastructure corridors, the short purple-coloured route shows the discharge pipeline location for treated mine water, which we intend using during the initial construction phase until mine wastewater is redirected to the operational process plant. The yellow route shows the pipeline infrastructure corridor, which is aligned with the proposed Northern Access Road that will link the Highlands Highway to the mine area. The Northern Access Road, in combination with the current access road between Damakwa and Bavaga and planned community roads going around the south of the mine area, will create an important economic corridor, estimated to open up and provide access to large areas of land for a variety of potential agribusiness activities, as well as providing improved access to produce markets and a range of social services for local communities along the Lower Watut Valley. Since 2010, WGJV has worked with farmers from Lower Watut and other partners to create a vibrant cocoa industry. This program has provided for the development of nurseries for high-yielding cocoa varieties for distribution to farmers, crop husbandry training, cocoa bean fermenting and drying training, quality control training, and marketing assistance. The development of new transport infrastructure will allow for further growth of agricultural enterprises in the project area, which would benefit communities and the region. A range of agricultural products including coffee, rice, cassava, biomass, poultry, palm oil and beef cattle are being explored by WGJV and agribusiness partners aligned with Morobe Province's Kundu Vision 2048 and PNG's National Development Plan. The Northern Access Road will include 2 large bridges, a 200-metre bridge over the Watut River and a 450-metre bridge over the Markham River. From near Zifasing, the infrastructure corridor will follow the PNG Power high-voltage transmission line corridor before travelling parallel with the Highlands Highway into Lae. Special care has been taken with the route selection to follow previously disturbed areas and minimise potential environmental, social and cultural heritage impacts. In general, existing farming practices will only be disturbed during the actual pipeline construction window and may resume on the edges of the pipeline corridor once the pipeline trench has been backfilled. All of the pipelines are designed with special protection against corrosion and have internal pipeline cleaning and inspection systems. Importantly, they also have leak detection systems. In Lae, the concentrate and fuel pipelines terminate in the port area, while the tailings pipeline continues to the outfall area to the east of Wagang. At the port, a concentrate filtration facility will be built. It will contain large filter presses that squeeze the water out of the concentrate to form a damp cake that is stored inside the fully enclosed storage facility ready for export. The filtrate water is treated to meet water quality requirements prior to discharge offshore. Concentrate will be loaded on a cargo ship using a covered mobile conveyor system. The ships then transport the concentrate to smelters around the world for copper and gold recovery. We now move across to the outfall area to the east of Wagang. Here the tailings pipeline enters the choke station. Its purpose is to reduce the pressure inside the pipeline prior to the tailings being discharged into the mixing and de-aeration tank. In this tank, we introduce 4 parts seawater to 1 part tailings mixture to increase the density of the tailings, because the tailings only contain fresh water at this point. The tank also allows any trapped bubbles of air in the tailings to be removed. Both of these things help the tailings to stay together and flow along the bottom of the seabed after discharge. This shows the location of the outfall system. An important consideration for the suitability of the proposed deep-sea tailings placement system is the existence of 2 major river systems, the Markham and the Busu. Studies estimate that these and other rivers along the northern shore of the Huon Gulf deposit in the order of 60 million tonnes per annum of floating, suspended sediment into the Huon Gulf each year, with additional sediment pushed along the bottom of these rivers into the Gulf. By comparison, the proposed discharge of tailings from the mine will on average be less than 1/4 of the existing natural sediment being deposited into the Gulf. The pop-up insert shows a cross-section of the tailings outfall system. In the left-hand upper corner, you can see the mixing and de-aeration tank. This is connected to twin 500-metre-long seawater intake pipelines that are shown in green and are used to collect seawater from a depth of 60 metres for mixing. The twin tailings discharge pipelines are shown in red and are 1,000 metres in length to enable tailings to be conveyed to the outfall location, which will be situated at a depth of approximately 200 metres at the edge of the subsea Markham Canyon. It is important that the discharge depth is well below the euphotic zone depth, which is the maximum depth that 1% of light can penetrate, effectively the limit that allows photosynthesis and biological production to occur. This is shown as the blue dashed line at 60 metres depth in the diagram. The second white dashed line, shown at 96 metres depth, is the deepest level of surface water mixing caused by wind and wave action that has been detected in over 12 months of monitoring. The Wafi-Golpu Joint Venture has utilised a 2x safety factor in the placement of the outfall at a depth of approximately 200 metres, which is well below the mixed layer. This is a very conservative approach so that tailings will not affect biologically productive surface waters, the coastal environment, and the communities that use them. At the outfall location, the tailings flow along the seabed and down the 20-degree average slope canyon wall, leading to the gently sloping bed of the Markham Canyon, where they mix with a persistent near-bottom suspension of natural river sediments coming from the Markham River. These further mix with other river sediments, including that transported by underwater landslide events, and deposit at depths over 1,000 metres. At mine closure, this same natural sedimentation will bury the mixed tailings and sediment deposits. We hope that you have found this informative and helpful to your understanding of the Wafi-Golpu project. It is a very exciting prospect for the future of the Morobe province and for Papua New Guinea, and the Wafi-Golpu Joint Venture looks forward to advancing its permitting and development with the cooperation and support of all of the communities affected by it. Thank you for listening.